Well, good morning. Thank you so much for coming here today. I know some of you have been traveling from far, far away, so it's super exciting to have you. Today we're going to talk about Kafka and Iceberg and some things related to how do we bridge in between the two. Anyone here is using Kafka already? All hands. Anyone here is using Iceberg? All hands. Okay, amazing. That's perfect. All right, no more fragile pipeline. How do we bridge in between all the data that we have in Apache Kafka and bring it into our analytics space, which is mostly used in Iceberg? Having said that, Iceberg is built on top of Parquet and other known file formats, so we have a lot of flexibility with what we're doing in it. I work for Confluent, and Confluent built a solution for that exact thing. If you don't know Confluent, Confluent is a data streaming platform company with thousands and thousands of customers. And today I'm going to dive into how we build it in-house for our customers. So you can take some inspiration, learn more about the challenges in between the two formats, and maybe even if you want to implement it in your own organization or think through some of the challenges that you might be facing. So what did we do? In Confluent specifically, we have Kafka topics. And each Kafka topics has a name, has some serial information in it. And essentially, we wanted to enable everyone that uses the platform to easily take all their data and dump them into Iceberg. So you can see in our UI, we have kind of like enable table flow. Table flow is the product we created. And we have this button called enable table flow. We click it, and the data goes in there. Inside, we have two formats that we're currently supporting. One is Iceberg with all the metadata required to start working with any catalog out of the box. You can think about Glue, you can think about Polaris, you can think about Unity Catalog. All of them, it's got all the information is going to be right in there. And the second one is Delta. If you heard about Delta, you know, mostly part of the Databricks ecosystem. Some people use it outside of the Databricks ecosystem. I'm going to say this about implementing that thing named table flow. Intuition here is not our friends. The first step that people think about usually when they want to implement, they think about Kafka connector or Iceberg connector or anything related to it. But the reality of the things is that underneath all that, magic, there is a distributed system, and things doesn't really operate the way we want it to operate. And so intuition is not a friend. If you heard about the Dunning-Kruger effect as well, really critical to think about it. We start in a place where we think, oh, that's going to be easy. I'm just going to write this SQL, but then we figure out that this SQL operations or this little bit of code doesn't really work. So this is what you see here is streaming insert, where we configure some of the cases to the connectors. This is going to break, and I'm going to go over why it's going to break, and I'm going to go over how we fixed it. So what are the challenges that we see when we try to use these connectors? One is consistency. Distributed system, consistency is always a problem. Second thing is schema evolution. My data changes all the time. How do I make sure it continues to be updated? Because as you've seen back then, we have kind of like a fixed schema that someone typed in. So we want to make sure we are enabling that schema evolution between the two estates. And lastly, small file and compaction. No one likes to run their analytics forever. No one wants to wait for hours and hours. And so small files and compaction is something that we must have in our solution in order for our friends in the analytics world to be able to run fast queries. And that brings me to the open questions that we went through in the engineering team. Some of the things we thought about were, how do I materialize the table? What do I do when the schema changes? How do I monitor all these jobs when they break? How do I make sure we have a good system to monitor these? Again, we're serving thousands and thousands of customers that has thousands of Kafka topics and Iceberg tables and so on. We really want to make sure we have a solid solution there. What do we do about bad data? Sometimes when we do kind of like type promotions and things like that, and we'll dive into it, sometimes the data changes and suddenly we have kind of like a null value in there. It's not a lot of fun. How often do we create these Parquet files? When I'm taking all my data from my Kafka brokers and I want to dump it into Parquet, how often should I do it? What is the reality of the things? What will make it simple for me to also think about compaction in small files in this? And lastly, we want to maintain this solution. We build it once, twice, and we want to continue having it running in production the way we intended for it to run. So what are some of the cost optimizations that we can do there? How do we actually schedule and run these things? Yes, again, a little bit about the intuition. It feels like an easy problem to solve. It's not. And there's tons of exceptions everywhere when you start working with that and you discover all the magic of distributed systems. And this is what we're going to unpack. A little bit about me. I wrote 2 books for O'Reilly. One is Scaling Machine Learning with Spark. Second one is High Performance Spark Second Edition. I spent more than 10 years in engineering, and after that I moved into management, and I've been in management for almost 7 years now. I started my career in the data and analytics, a little bit of classic machine learning, if you know that world, and then I moved into data streaming, so my background is kind of like diverse across the data ecosystem. So if you kind of hear me saying things that sounds a lot like analytics world, that's what it is. But of course, I'm going to use terminology that's related to data streaming as well. So our solution that we build, and I'm going to show you the architecture, serve trillions events every hour, gives us the Kafka to Iceberg, Kafka to Delta Lake, and trillion multi-version schemas for our customers. So let's start from the beginning. A lot of you mentioned that you already work and use Kafka, so this is going to be a quick reminder. Data is being, with Kafka Producer, data is being serialized, saved into a Kafka broker. In my Kafka broker, there could be many topics that I have in there. And lastly, it's being consumed by some application or maybe even solutions like Apache Flink and so on down the road, and the data is continuously being processed. Now, the challenge with one Kafka topic, when I have it, Kafka topic is kind of like agnostic to the world. It can have anything you want to put in it. So it doesn't care about the version, it doesn't care about the schema. It kind of, it's agnostic. Give it whatever you want. It will take it and pass it. You can use the same topic for multiple schemas, for multiple versions, and so on. And this is where schema evolution starts to be a little bit more complicated. So, what do we do, and how to update this table specifically when schema changes? Because Kafka has no schema, Iceberg definitely has a schema, and we need to bridge the two. So there are different formats, edge cases that we need to think about. There are semantics of tables that we need to think about, things like append, upsert, and so on. Dealing with bad data, automatically inference of schema. This is something that we are familiar with and are able to do. And we want to convert and maintain that divide between Kafka and Iceberg. So how do we do it? When we have key value records of bytes, right? Kafka on my left side has key value records of bytes, common data formats that are available for me to use when I'm using Kafka, Avro, JSON, protobuf, and so on. On the other side of the world, I have very structured tables, SQL data type, tables with columns, rows stored in Parquet, and so on. And I want to bridge in between them. So I want to have some schema evolution when I'm taking those bytes and running some deserialization on top of that data. And I want to enforce some of the schema evolution related to them in my Iceberg. So when I have multiple versions, I want to start thinking, well, who can I rely on to help me manage all these multiple versions that I already have in my system? Because, for example, V1, value 1, can have only one column. Value 2 can have 2 columns, call 1, call 2. V3, you already realize that we have multiple data in there. And this is where we're starting to rely on something called schema registry. Anyone here heard about schema registry? Yes, a lot of folks in the Kafka space. Amazing. Schema registry helped me manage schemas and manage versions and help me with schema evolution. Essentially, it gives me the tools to enforce what is happening in between the producer and the consumer all the way through. So if something bad happens and it's out of schema, I'm able to send that data into a deal queue, for example. So this is the first step that I have to do in order to bridge in between my Kafka world and my Iceberg world. So this is one step. It had 3 different compatibility modes. One is backwards, which means consumers can read previous produced data. One is forward, which means consumers using old schema can read the newly produced schema. This is really important. And the second one is full, both sides, essentially. And it all works through the serialization, deserialization process that we know exists in Kafka. Like I mentioned before, if something is out of schema, doesn't work as I expected, deal queue is the pattern that I'm using, essentially meaning I'm sending it to a different Kafka topic. Later on, I can monitor and put the alerts, and that's going to help me with maintenance and reliability of my system. Now let's talk about schema management in Iceberg. Schema management in Iceberg works completely different. For the exact reason that it's automatically in storage, it was built for analytics, it wasn't built for streaming. It was built with schema first mindset. And so specifically in Iceberg, what we have, you can see the data layer all the way at the bottom. It holds the actual file. One step above, we have what we call the metadata layer. Metadata layer will hold some records related to the snapshot, related to the data that later on points. There are pointers all the way down to the data layer. And at the top, we have kind of like the data catalog itself, the current metadata pointer, what's the table that exists, what the version that I can support, and so on. So when we're accessing data through Iceberg, essentially, it's going to search for where the right file to give us, the right file to read, through this hierarchy of schema management. Now, Iceberg gives us the ability to run automatic schema evolution. We can add new columns, like most of the analytics space. And column deleted are marked in null. They're not really being deleted right away. There's some process around that, around vacuuming of that data. And it supports type promotion. Type promotion is highly known in Parquet. There's different type promotion between Parquet and Avro format. We'll touch on that in a second. But it supports type promotion. This is something to remember, because if I have an int in my, let's say one of my columns is of type int, I can later on put long value in there. It's going to update this column to be long, and it's going to continue having that as a long. And this is something very interesting that a lot of people tend to forget, but schema evolutions enabled us that. And of course, it supports float to double. So how do we decide which schema to use? Now that I have my Kafka inside my topic, I can have multiple schemas, but I want to take all this topic and transform it into a table. So how do I know how to go about it? There's a couple of ways to go about it in engineering. One of them is stop the world. Anyone here in engineering ever did a stop the world thing? Where you completely stopped everything, nothing is going to change, nothing what is in production, maybe we need to pause production as well. This is a very risky step to take. You have to convince a lot of executives out there that it's going to make sense to stop the world for your customers. Extremely risky, not something to think lightly of. If you are taking these steps, it means you have a real big problem, and it's okay. But there are better ways, and we'll go through it. Second thing is ignore bad data. A lot of people just drop rows, just drop events, just drops entries that has the wrong format in there. Again, this is an option, but at the end of the day, what we're getting is data that is not exactly complete. And this is another problem that we want to face. And if we're doing it, we have to understand that, for example, we're not dropping bank transactions, for example. This is going to end up bad results. Third thing is write to deal queue and fix later. This is a solid option that many of us use, many of the people that I spoke with in engineering use. It makes sense. I have something, I don't know what to do with that. I'm putting it in a deal queue, and later on I'll create some alerts. I'm going to wake up in the middle of the night and I'm going to fix it. But we'll know exactly what happened, and we'll have someone monitoring your system. And lastly, probably the best way of what we build in Confluent is adapt the schema to handle the change. So now my schema, I'm adding some guardrails to it, and my schema knows how to run this evolution automatically. Of course, with alerts, of course, with the exceptions necessary, but my schema is well supported. So how do we do it? First of all, we convert the latest schema to a schema registry. We know now all the data that I have in my Kafka topics is attached to some schema registry. I have information about what exists in that data. Second thing is we created an Uber schema, which means if we have type evolution, if we have any changes to our data, we're taking the row, we're taking the entry with the longest numbers of values in it, and we call it, this is our Uber schema. We understand that some values are going to be non-existent. The data could be sparse overall, but this is fine. This is something that we're willing to do, and it gives us the ability to automate this process. So you can see here in the example, if I have different types, V1, V2, V3, V4, I'm taking the maximum. So address byte, now I have two addresses in here. One address string was address with array of bytes. I'm deciding to take address, and address byte is yet another column that I added into my system that supports bytes. This is how we solve specifically and everything related to schema evolution. Second challenge is consistency. We're talking about distributed system. We want to make sure that all the data was written exactly once in between these states or have some mechanism to control it. So what do we do in how our Kafka is built? Our Kafka is built slightly differently than the open source solution, as you can imagine, because we're supporting thousands of customers. And so we have something like object storage where we save some of the data up there in the cloud. It requires a different type of latency. So if I have my Kafka cluster, I have a lot of topics coming in. I have a local storage that is on the machines. We're actually tracking where the rack and where the compute and where the exact data is at. And then I have my object storage somewhere in the cloud. My TableFlow service, what it's going to do, it's going to call my Kafka cluster and it's going to ask to fetch some data. So it's going to ask to fetch the specific topic. It's going to ask to fetch specific partition and register the exact partition that we fetch the data. And it's going to ask to fetch the start and the end. What's going to happen after that? Some of the segments that exist there are not necessarily on the local storage. So my Kafka cluster is going to reach out to the object storage. It's going to ask for a request to fetch a specific segment of the data that we need to bring back to TableFlow to write it into Iceberg format. It's going to return me some location to read, and then all this communication, the data doesn't pass through Kafka cluster. We don't want to create this bottleneck on Kafka cluster like Kafka Connect and other tools does, but we're returning a pointer. We're returning the location, the URI of where to fetch that data from. An important point, because if you are asking Kafka cluster to pass that data as is, you're creating a bottleneck. Don't do that. And so now that TableFlow has the location of where to read, it can communicate with the object storage and ask to bring back that information. Some of the things that Kafka and both TableFlow needs to know, this is critical information, is exactly which partition and what is the offset that we need to bring the data. Topic partition arrangement, how does it look like? There is a mapping between topic partition arrangement to segment. If you look deeper into the Kafka world, you'll see that. And it gives us a better possible serialization because we're passing the URI, we're passing the location, we're not passing that information through Kafka. So how does it work now that I have my information there, I know where the data to bring, and I want to dump it back into my Iceberg? So Iceberg has its own way of maintaining consistency, and it uses a lock mechanism. So there's something called optimistic concurrency control, optimistic concurrency lock. It means that the data that is being written all the way downstream is kind of locked on a specific area. So one writer can pass, so this is how we kind of avoid conflicts. So one writer can pass, and it checks conflict at a time. I'm not going to dive into it. It's an interesting algorithm if you want to dive into. But again, slightly different than how Kafka is doing consistency. So how we connected all the things. You've seen the TableFlow. We're now breaking it down. Inside my TableFlow, I have two services. One is Materializer, like we talked in the beginning, something that materializes my data, help me understand what exists out there. It brings in the segment. It knows how to call my object storage. And then I have committer, because I want to make sure it was exactly once that all the data was committed and written. If anything happened throughout that integration with my object store to write back to Iceberg, of course, all the process is going to fail, and we're going to revert back to the previous state in order to fix that and make sure we have high consistency in it. So you can see here, uploading Parquet file, committing the task to the committer, and then a follow-up of latest commit offset with the information that we just committed, and this is how we're maintaining the loop. So we talked about consistency, and we talked about schema evolution. We're going to talk a little bit about small file compaction. There's a lot of problems around small files in the analytics world. Essentially what it means every time I want to do read, it's going to take me longer because I/O access. That's physics and the nature of things. If we're diving into, for example, Unity Catalog, you can see how the Unity Catalog works, kind of breaks down between the metastore to the catalog to the schema and so on. But what's really interesting, and underneath any Iceberg table that I have, is actually the Parquet structure. which that means that I have to, if I have small files, I'll need to access more Parquet structure, more files essentially, and I have to go through reading all the magic number, the row group, the version schema, and so on, and this is very extensive I/O that I don't want to face. So what are the compaction strategies that are available out there? There's tons of them, really. There's bean packing heuristic algorithm, trigger conditions, size-aware policies, metadata table compaction, partition-aware compaction. There's a long list of things, and we research each and every one of them to understand what makes sense for a streaming kind of solution that we build. And we landed on trigger conditions specifically. Trigger conditions, once there is a specific threshold of data, specific threshold of information, I can decide to now trigger the compaction, which means if I didn't reach that threshold, I'm not going to trigger it, and that's the best solution that we have when we're bridging in between data streaming and analytics. It's easy to implement, and simplicity here is key when you're building distributed systems. You don't want to create too overcomplicated algorithms just for the sake of overcomplication. We do want to make it simple, we do want to make it easy to maintain, and we do want to make it intuitive. And so number of files, size, threshold time was the best algorithm that we at Confluent decided to go with. There are some necessary optimizations that we also implemented in Confluent for our customers related to Iceberg specifically. One is pruning alt snapshot, what we call vacuum, and so on. We want to make sure we're helping customers with the data there as well. Garbage collected of unreferenced files. If I deleted some things, Iceberg just leave it out there, so we want to make sure to garbage collect it. Compaction of the metadata file. You see how complex the metadata of Iceberg. We want to make sure to run over that metadata and update the compression there as well, as part of the compression process that we're running, and compact of data files itself. So, closing up, we have a couple more minutes. This is how we build it. We created that kind of like a button, and we implemented it for both Iceberg and Delta Lake. Let's do a quick recap. So what did we talk about today? We talked about bridging in between two distributed systems, one heavily used in data streaming, one heavily used in analytics space, which are Kafka and Iceberg. We talked about why the connector doesn't work and how it creates a bottleneck on top of the Kafka cluster. We talked about type promotion, how it doesn't take into consideration when the different types in between my Kafka, for example, Avro, when we're doing type promotion, is different than how we're doing type promotion in Iceberg. We talked about schema evolution, how Kafka topic can have any schema in the world that it wants. It's kind of agnostic, it's kind of schemaless. And so adding solution like schema registry helps us make sense of what exists in the data and have some, beginning to control of kind of guardrails of what is in there in that black box. And how Iceberg, on the other side, has its own schema evolution process that is slightly different and supports kind of like more of the analytics world. And we talked about file compaction. We talked about different strategies for file compaction, like the bean bucketing and so on, and the threshold. And I shared with you how we decided to go with specifically the trigger one, because the trigger ones enables us to keep solutions simple and also don't mess with the data. The rest of the solutions are kind of a little more statistical, are more depends specifically on the data that exists in there, and we decided not to look into what exists in the data. We don't care about it. Again, creating a solutions for thousands and thousands of customers means you cannot become specific about the type of data if you have IP data or any other data in it. And so the solution that we went with is the trigger one according to the size and the number of files is the best solution, and also the simple solution to implement. If you're interested in that, go implement it. It's really easy. Or you can try out Confluent. It's something interesting to you just to play and get the feel, and then if you want to implement it later on, you're most welcome. There's a ton of resources. If this topic is of interest to you, there's a lot of ways of how you can learn and educate yourself on this solution and how to build it. Of course, starting with kind of like the fundamentals of distributed system, how to go about that. What does it mean, when you want to transfer some information in between different services there? How do you ensure consistency in a distributed system, as well as some of the things that we build in it? So there's 2 great talks also on that topic. They dive into different areas on that world. There's also a wiki page that we created, and there's also another talk about small files that dives into why small files are probably the biggest problem in the analytics space that we're suffering from. Yeah, and that's it. Thank you so much for listening in. I know it was a lot of information all at once. I hope you'll enjoy Big Data London, and thank you for being a great audience.